is our first ever pre-doc, this young punk kid from Harvard who called up and said he wanted to work with us. What can we say? I mean, Harvard's great, so, and he's certainly a chutzpah, and so we invited him to work with us, and he and Hamid did brilliant work with a host of other people for about a year and a half, just a year. And then he went on to grad school at Wisconsin and eventually to fame and fortune. I was going to say something about Wisconsin at that time was the best database school in the country, and Joe has now been one of the ones arguably making Berkeley the best database school in the country. And I say arguably in case anybody on the phone wants to argue with me. Okay, so I'm supposed to do this fast. I will, beyond that, just say that Joe has done brilliant research that I deeply admire over the years. He's continued to do really wonderful stuff. He's a fellow of the ACM. He's had a Sloan Research Fellowship. He's made all sorts of magazines, smartest people things, and he's got 3 Sigma Test of Time awards, and I'll shut up and sit down.
There you go. Thank you so much for having me. It's such a pleasure to be back. Warms my heart and to be here with my mentors. So thanks to all of you guys for having me and for all your help over the years and inspiration. We have a kind of pixelated version of the talk today, it appears, but that should be okay. So if we manage to get through a bunch of this, there's actually 2 talks here. We'll just do one of them and solve our problem. So these are sort of an amalgam of a talk I gave at the IEEE Big Data Conference and a talk I gave at ACM SOC over the last month or 2. There's an introductory piece where I'll talk about the deal with the devil that we're all involved with. There's a second piece on distributed programming, sort of our results on the Calm theorem and a language redesign called Bloom. And then the sort of second talk, or the third section, which we may or may not get to, is on wrangling data and building new modes of interaction for people to work with data that are much easier. It's also the genesis of my startup company, Trifacta. So we'll see what we get to. And
So that last one is really interesting.
it is really interesting. To this part. It's also the shorter part.
I just
Okay. You can kind of jump back and forth, I guess. Let me put a little context on this whole business. And I'll do it quickly. So, in fact, I'm going to kind of skip these slides. Let me just say this. Computers are cheap. Data is abundant. Everything is free to a first approximation. You can build a lot of compute for very little money. The only bottlenecks left are people. So, rather than give you a whole lot of stuff, we have everything we want, right? But it is sort of a deal with the devil, in the sense that it's not as if actually having all this compute for free is easy. What we're giving up is essentially all our illusions about what it means to program and work with a computer. So everything that we understood about what computing is has kind of gone out the window. Sequential programs are no longer really what we need to write because all of our code is distributed. This notion that there's a single copy of state is no longer true. The notion that we're building machines out of reliable components is no longer true if it ever was. And the notion that data will be carefully modeled and managed is also not true. So none of the things we assumed when I was taught computer science are true anymore. It's nice that we have all this hardware and all this storage, but it's actually a pretty miserable phase in the environment or the history of being a software developer. This is kind of crazy. That's where we are. So yeah, so it's a misery, right? It's all human cost now. Everyone's doing distributed programming if you're a developer. And if you're working with data, you spend all day long wrangling your data and you don't ever get to do anything quote unquote interesting. The people who are good at this stuff are wasting their time doing things that should be easy but have turned out to be hard, like formatting data sets. And the people who maybe you'd like to have doing those things can't because it's too technically difficult right now. So this is the biggest challenge of computer science today as far as I'm concerned. Making things go faster is all well and good, but I feel like I wasn't getting any more brownie points for that, so I gave up. Things will go fast, that's great, that's awesome. Somebody else can work on that. We need to work on making people more productive. Here's one thing we can look to for inspiration. So Alfred North Whitehead has this great quote, which I think I learned from Guru Ramakrishnan. We were putting together quotes for his textbook. So this is the quote: "By relieving the brain of all unnecessary work, a good notation sets it free to concentrate on more advanced problems and, in effect, increases the mental power of the race." So if we could get something like this going for ourselves, if we could get the right way of expressing what we want to do with all these computers and all this data, we'd have a huge leg up on these problems. So at some level, this is a language or notation problem, right? And that underlies a lot of the work that I taught. I also discovered totally randomly yesterday on Wikipedia, Alfred North Whitehead is the fellow, among his many accomplishments in mathematics. The notion of creativity is due to an essay he wrote. That word and the way we conceive of it is due to Whitehead. It's kind of interesting. The whole idea that there's a thing called creativity comes from a like polemic he gave. Just tripped across that on the internet. Okay, so perhaps one of the keys to making these things better is to stop thinking about general purpose programming and think a little bit more about domain-specific programming and domain-specific languages as a way to get a leg up on some of these challenging problems. So the idea of a domain-specific language is that we raise up the abstraction level and we get people writing high-level code that is in a small language that's not fully powerful, and it's in some sense customized or bespoke to the environment we're in. Some of those languages were invented right here. So SQL is often the first example of a domain-specific language that people bring up. But Visual Basic for applications, Lex and Yak, LaTeX, and on and on. Right? So these are all examples of domain-specific languages. And if you go read what the PL people write about domain-specific languages, you can't see this because of the screen, but Paul Hudak's sort of, I think it's the Handbook of Computer Science essay on domain-specific languages says, here's the good things about them. They're more concise, they're quicker to write, they're easy to maintain, they're easy to reason about, and they're accessible to non-programmers. Well, that sounds nice. And here's, I think, the point that is well expressed. A user who's immersed in a domain already knows the domain semantics. All the DSL designer needs to do is provide a notation to express the semantics. Just let me say what I want, what I'm thinking. Right? Don't make me write for loops and where clauses and whatnot.
People actually compare with SQL, right? So people actually put logic into applications and nowadays.
So in fact, if you look at this list, Shankar's absolutely right. Almost none of these languages are accessible to non-programmers. Arguably, every single one of them fails in that goal. So there's landmines ahead. If you think you're going to write a little language, I think what you've learned is it can get to be pretty complicated pretty quickly. So yes, absolutely. Still in all, and sort of this is my point, this sounds easy. Okay. Still in all, I believe that DSLs are the underpinning that will allow us to have better interaction models for wider use. We'll talk about that. So big data is great because big data gives us sort of two user personas in these little sort of prototypical environments where we can study what's going on. So developers, all the problems that developers face about distributed systems are kind of typified in this NoSQL environment. And all the things you could build that would make life difficult for application writers exist in NoSQL. They're like, pieces fail, and they don't promise you any consistent memory models, and you don't know what kind of performance you're going to get. That's all baked in there. So people are dealing with that today at sort of developer level and struggling with what it means to write distributed programs. And then this kind of Hadoop ecosystem's got all these data analysts dealing with raw data that they can land in a file system and trying to get some use out of it. So there's also this sort of petri dish of how will people work with data when it just comes at them for free over on that side. So kind of the two sides of what we think of as big data provide us with sandboxes to play with I think, these burning issues. And so it's actually fun times in a way, also because these technologies are so immature, to rethink some of these things. Right? And everything's very fluid today. So the talk kind of breaks down into those two pieces, and Laura was telling me that you guys might, in this audience, be more interested in the sort of data management side than the distributed programming side, or distributed development side. Or Laura's more interested in that. I wasn't going to go in that order because the results in the second part are more fundamental. Ron will like the second part. Can't think. I hope. Already won't. That'll be worse. But it'll be interesting. I'm going to go straight through. All right, so this is the outline of this section. So we talked about things being a deal with the devil. I'll talk a little bit about, well, I'm not going to read the outline. Let's just keep going. So if you're a developer today and you're writing anything interesting, there's a distributed system behind it. Even if you're writing mobile apps, there's a distributed system behind it. Okay? And distributed programming is hard squared, is what that says. Designed for the X. So you got all the problems with software engineering, which was already super hard and expensive and complex. And now we're multiplying that by parallelism, asynchrony, and failure. all things that make programming really difficult. So you have two choices, right? You've done this deal with the devil, right? We're programming in this difficult environment. Choice number one is you can dance with the devil, okay? So you can say, I don't care, you know, I got these crazy computers, I'm just gonna make them go fast. And we'll see what happens, right? And roughly what we'll do is we'll just write distributed programs, but we'll write them in a coordination-free fashion, and we'll just sort of ignore that they're distributed. So we'll write sequential code in languages like Java, and it'll run on each box. These programs will communicate asynchronously the way they would without waiting. And you know, we'll get that full scope computation. We'll get all the bandwidth of our compute. Messages get to be pipelined on the network because we're not waiting for responses. So we get full bandwidth on our network, and all is good. You can do that, and then you just have to keep in mind that there's this risk that these are kind of non-deterministic. Messages may get delivered out of order, nodes may not receive them, nodes may go down, things may have unpredictable interleavings across machines. Okay, how bad could that be? A little non-determinism, kind of nice. Maybe you don't know exactly what your computer is going to do, but okay. I mean, sorry?
You wouldn't anyway.
You wouldn't know what your...
There's plenty of non-determinism for everybody. It's already there.
It's already there, so why not just keep doing what we do?
Yeah.
You know, and maybe the worst risk of just plain old non-determinism is, you know, when this guy gets really mad, there's my animation, he splits your brain, right? So now you've got a system where there's state that's stored in multiple places and it disagrees with each other, and the system over time kind of is inconsistent in a permanent, unfixable way. Okay, so these are the risks you face. And maybe you can write your programs in a way that will deal with these risks, and we'll talk about that, because developers are spending lots of time writing applications that can deal with this environment. And the other option you have is to pay the devil his due, which is to actually work for consistency and to coordinate these machines pretty often in order to get them to agree on stuff. But coordination, frankly, it's the last expensive thing in computing. And maybe it would be a good idea to pay the devil his due, but this stuff is really expensive because now you've got all this hardware and waiting for each other, and you end up at the mercy of the tails of your distributions in terms of performance, right? So now you're not getting the bandwidth of the machines because you're waiting on things that are probabilistically unlikely but happening all the time at scale. So maybe you can do this, but lots of people say you shouldn't. So one of the people who says you shouldn't is your friend James Hamilton, who used to be, of course, part of the IBM family. So he had this great, there's this great quote from a talk he gave back in '09 at a cloud computing conference. The first principle of successful scalability is to batter the consistency mechanisms down to a minimum. Move them off the critical path, hide them in a rarely visited corner of the system, and then make it as hard as possible for application developers to get permission to use them. Right? So he's basically saying, dance with the devil, damn it, you're not even allowed to pay. Right? That sort of was Amazon religion, at least circa 2009. So, but maybe we should pay the devil. And a lot of people talk about, hey, you know what? Distributed transactions have been solved because Google had a paper saying they built a distributed transaction system. So if it was Google, then they must have solved the problem because those guys are smart. It's weird how they get credit for that stuff. And then you go look at the numbers. Okay, so these are the latencies on the spanner system, which does geo-distributed transactions with a certain consistency model. So a multi-site commit, the mean latency to commit is 103 milliseconds. Right? Think about that for a second. If you're doing anything that's worth coordinating, it means that there's other things that are contending with you. Otherwise, you wouldn't have bothered with coordination, okay? So we have contended resources, each one of which is waiting for the other, which means we're waiting for things that take 100 milliseconds, which means that we're getting a throughput of 10 transactions per second, okay? I assure you that very little of Google's experience that you have with it runs at 10 transactions per second, right? So this can't be getting used very much. This has been, you know, James Hamiltonized. It's been shoved into a corner of Google where it's very rarely used, and almost none of the systems get to call this stuff because it's ridiculously slow, all right? And one of the reasons for that is look at the standard deviations. They're even bigger. And in the comments in the paper, they talk about, look, the standard deviation of write latencies is caused by a pretty fat tail of the distributions due to lock conflicts. And of course, that's just evidence of what we already knew, right? That we're dealing with the devil. If you pay him his due, you will see him pop out here. Okay, but let's, you know, maybe you could do better. Maybe you could do better than Google. They're really not this smart. You guys are IBM, right? So my student Peter Bayless went ahead and tried to model, you know, based on analytical model with numbers he'd gotten from industry of local transaction performance, and then measurements you can find in the literature on both data center and wide area network latencies what's the maximum throughput, sort of theoretically, that you could get to do one or another of these two-phase commit protocols? And the throughput's not good. The throughput's kind of like what Google's seeing, okay? And you know, it's because of the speed of light. If you're going to do global transactions, you get to do 7 round trips around the world a second. That sounds familiar, right? With 10 transactions a second on order, right? Google guys are doing pretty good, relatively speaking. They're getting their photons moving really fast. Okay, but it's a problem, right? So you're just not going to build these things. You're not going to use them. You can build them, you're not going to use them. Okay, so it's pretty fundamental. And of course, don't forget variances make it worse. Okay, so this is a big question when you're writing a system. Do you dance or do you pay? That is, do you run without coordination and risk inconsistency, or do you pay for this coordination at this incredibly expensive cost, the wide area, somewhat less expensive cost within the data center? And more sadly, if you're building an infrastructure or a service like Google or any other hosted service, which parts of the system coordinate and which don't? How do you make these case-by-case decisions as a developer? And kind of scarier, if someone over there is doing sloppy stuff, is that going to taint your carefully designed stuff and make the whole point of coordinating pointless? Because there's taint seeping into your code. These are hard problems. So the takeaway from all this, and a little bit of foreshadowing where the talk is going, coordination is like the only expensive thing left in computing. All right? A big question is, when can we avoid coordination without getting inconsistency? So the Calm theorem is an answer to this question. What can we compute without coordinating? And then secondarily, given what's possible, how can we avoid that coordination? And the answer, interestingly, is not going to be to think about reads and writes. It's going to be to think about application level semantics. Okay, so I'm going to skip this stuff. Point out that all of our problems come from the von Neumann model. Okay, so the von Neumann model says, there's mutable state is at the core of this thing. The Turing machine's got the same problem, right? Mutable state is the key sort of element of this system, which gives us this huge primacy of ordering in these things. There's a list of instructions in von Neumann that you tick through with the program counter. There's this array of memory that you mutate in time, which is a total order, right? So it's total orderings and even partial orderings. They're just all over the place in the way we talk about computing. When you tell a non-technical person what an algorithm is, you tend to say it's like a recipe. First you add the flour, then you add the eggs, then you stir, right? We think about this stuff sequentially. It's been baked into our way of talking about computing for almost a century, it feels like. And it's all the same stuff. Right? Sequential computing, single copy state. This is the von Neumann model. All the things that are not true are our mental model of how we compute. That's a problem. So, I don't know if you guys are young enough to enjoy this. So there's kind of 2 ways people have responded. I alluded to this. There's sort of the bottom-up kind of operating systems flavor of this, which is, well, maybe we could get other guarantees at the read-write interface. They're weaker than, say, linearizability or serializability, but there's something. Maybe we can get you causal consistency or some strange weak isolation model for your transactions, or Doug Terry-style Bayou session guarantees. Maybe we just give you new building blocks and you can figure out how to write programs with them. But they're going to be very subtle because you no longer have this nice illusion of sequentiality that transactions give. Or, sort of the other approach is the application-oriented top-down approach. I have an application, I understand its semantics, and I will now realize that application over this inconsistent storage. And we'll go through an example of this with the Amazon Dynamo shopping cart implementation. There's a third, very strong contingent of people who are sort of the know-nothings. They're like, consistency? Why worry? And there's a lot of that going on in the industry. And interestingly, so again, my student Peter Bayless's first class project at Berkeley was, he went out and both modeled and measured what's the likelihood of inconsistency in these key value stores, in these NoSQL systems, both in the local area and the wide area. And he got performance traces from Yammer and from LinkedIn on their machines. And he was able to show that at least in the data center, if you use SSDs, actually like, 95, 98% of the time, you're likely to read an up-to-date copy of the data. So you can get lucky pretty often. But then you say to yourself, well, what's the workload at LinkedIn like? They're going to run into the bad cases with some frequency. So you still have to write all the exception handling code. So it makes you feel better up to a certain scale. Maybe if you're Yammer, it's okay. But if you get to be LinkedIn, it's a problem. Okay. So anyway, there's much dispute in the developer community, and I took out this awesome Twitter thread that I had between these developers arguing about this all the time. And the truth is that all the people arguing for these points often are right in their arguments, but from a pragmatics point of view as well as from a formal point of view. And so it's really interesting times to kind of attack this from all these directions. But I think the key thing is that we're sort of dancing on the wrong bottom, that this von Neumann assumption is just not the right place to start. Now the top-down stuff can be made to work. People really do build consistent apps on inconsistent storage. And there's a lot to be learned here from what developers are doing. And I'll take you through some of that. The thing is that our bottom-up tools we give them are not helping them do these things. So we're still giving them sequential languages. Most of the stuff these days is written in Java. All right? We're giving them debuggers that let them step sequentially through code and see how state mutates, which is just the wrong way to think entirely. And test harnesses that do things like random fault injection into a space of permutations of activity that's way too large to randomly test. Right? So the tools are all wrong. If we had better bottom-up tools that admitted that we're not in a von Neumann world, maybe we could do the top-down stuff much better. Right? Where we are today is you get end results that are kind of hard to test, hard to trust. As a QA issue, it's really very expensive. So takeaway on all this, the von Neumann model underlies our bottom-up thinking. It's a terrible match to the cloud and so on. What can we learn, though, from these top-downers here? So the Dynamo paper is this sort of early NoSQL paper from Amazon. It gets cited a lot by people who are interested in NoSQL. And most of it's kind of boring. So most of it's about how you might build a distributed key value store with replication. And it's pretty straightforward. The interesting bit is the application they built on top of it that they measure is actually kind of clever. And it roughly works pretty efficiently without worrying about the inconsistency in the system. So the example is the Amazon shopping cart, all right, the thing that you put things in, that interface you have when you shop at Amazon. How do you do that on this mutable key value store? Well, if you start thinking about it, it's replicated database, keys and values, or replicated memory. And you really need to worry about all these consistency issues. So you need to worry about coordinating your reads and your writes. They don't build it that way. Actually, the way they build it is they accumulate a log of shopping events, and then only at checkout do they tally the contents of these logs. And the log is what gets distributed. The event stream is what gets distributed to the endpoints, so that each of the endpoints can work on that log separately. So briefly put, there's a client that adds and removes items. They go to some replica of the shopping cart state. There's lazy replication inside Dynamo between the replicas of the shopping cart state. Eventually, the client issues a checkout request and gets a checkout response to one of the replicas. All right, and the way you build this on a key value store is, you have a put interface and a get interface. It's basically a memory. And what you put is the item and the count of amounts of that item you've bought so far. So, here's how this would work. Two replicas, in this case, of the shopping cart. You come along, you say, I would like to buy the first apple, and you send that to both places. One of them gets it right away, the other one it gets lost in the network for a while. Okay. Then you say, I would like to buy the first orange, and that goes both places, so we're still doing pretty well. And then you'd say, I'd like to buy the second apple, and that actually goes both places, and we're still doing well. So this is kind of nice, until you deliver that lost message in the network, and now we have inconsistency. All right? So this is kind of the straw man implementation. If you did this, the way the interface is asking you to do it, and so the right way to do it in the literature is to coordinate, right? So just this is a little bit of a pedagogical exercise, but the way you would do this sort of, if you're a read-write person, bottom up, you're like, well, geez, we have to fix this. I'll give you a consistent key value store, so you don't get into trouble. You can't shoot yourself in the foot. So what we'll do is a round of Paxos or two-phase commit for every write, so that everybody agrees on the contents of the writes. And so it's going to kind of look like this. Paxos essentially gives you the illusion of a global clock. Everybody's going to wait till they all agree, and then we'll take the clock. So you buy that first apple, and essentially everybody waits till it gets to both sites. So the whole example that we had before, that period of time will pass. So both sites get an apple, and then the global clock is essentially ticked. And then we do it for the oranges, and we do it for the second apple. Those clock ticks are distributed coordination. They're very expensive. Right? But this is the way you would fix things if you sort of did it bottom up with the read-write interface, the way that database folk like to do. Okay, so the way that actually the Amazon guys do it is this sort of disorderly cart. That's the way we talk about it, with a no overwrite event log per session. So there's no state mutation. It's just accumulation of events. What we're going to do is append, not overwrite, but append data to these carts. And what we're appending are the actions. So we append buy an apple to both carts. One of them gets delayed. We append buy an orange to both carts. We append buy another apple to both carts. And eventually we deliver that first apple there. At some point, we also append a please check out. Okay? And at the point you get that checkout, now we have to do a little round of coordination to make sure everybody agrees on what we're checking out. All right? And after that clock tick, we're good. But we only did it big O of the number of times you say buy, which by the way had to go to the credit card system and a whole bunch of other expensive stuff anyway, inventory and so on. We didn't do it every time you added something to the cart.
They don't coordinate.
They don't
I
coordinate
mean,
at
if
all.
they don't match.
If they don't match, then that round of coordination for checkout will wait. And if you have timeouts, you can have it fail. You can send it back an error. But typically it'll wait for some period of time and hopefully succeed. But that's your 10 per second kind of deal. But hey, that's probably okay for checkout because you had to do all that banking stuff.
They could have each lost an apple, and they'll each think they had one apple, but really it was two apples. Two instances.
Well, you have to decide what you're coordinating on. And let me actually show you the next protocol, which actually has no coordination, and you'll get a hint of kind of what you want to do. So the coordination free card, which is actually not in that diagonal paper, but is what my students came up with, is pretty straightforward, actually. Again, we'll use a no overwrite event log per session. But the source of the coordination is not going to be a global consensus round. It's going to be a manifest that comes from the client. So there's a central point of knowledge, which is actually, in this case, the client. They know everything they bought. So they can send you a manifest. Here's all of the stuff I bought. And then there's a purely sort of local decision to be made at each site. Have I gotten everything yet? If there's everything in the manifest here, then I can check out without talking to anybody. Right? And so these replicas, hopefully over time, will check out. And the answer, I guess, to Rod's question is sequence numbers or some other thing or the way this is usually done, but there's still coordination. But if you do this right, you don't need coordination at all. Yeah?
What if you change clients before you check out?
What if you...
Change clients before you check out. I mean, on Amazon, you can log in on a PC, then check out on your phone.
That's true. That wouldn't work in this
And then it's
case.
going to have to coordinate.
Then it will do it wouldn't need to do the coordination protocol. You're absolutely right. Now, one way to do that is the new client can get in contact with all the sites, get a copy of what's been done so far.
Right.
And do consensus
Do a
when you log
consensus.
in. And then
Right,
you
force the
get-
client to do that.
Yeah. But you know, oftentimes the right solution to not doing consensus is to do it once and get the state into one local place of control. The client becomes the master.
This is coordination between replicas of the same card. What about coordination between replicas of different cards? I mean, you have a fixed inventory, fixed set of items.
Yeah. So delightfully, this paper, these Amazon guys don't talk about inventory checking at all, right? Which is an interesting problem. And then you get into yet another level of conversation, which is about if you want to run without coordination in those cases, oftentimes the engineering solution is to go extra computational. So you say, we might run out of stuff we promised to ship you, and once we figure that out, we'll send you a coupon or something, right? There's business logic that's kind of outside the computing framework. It's not solving the problem. It's not a true inverse of what you want it to do. It's some sort of semantic inverse in the real world. We'll make it right with you somehow, right? And a lot of computing has that. And so, you know, frankly, there's a lot of society, right? Law enforcement and doesn't enforce the law. Actually, there's the courts and all those remedies, right? So, and you know, you can kind of run this conversation further than we probably want to go.
Yeah.
But it's an excellent point, and it's only one step away from here. And every system built like this has to either coordinate or deal with compensations. So there's a really fun paper by Dave Campbell and Pat Helen called "Building on Quicksand" that talks about these issues and the one you just brought up as well. Which I don't have time to go through. But it's a very atmospheric sort of developer folklore kind of discussion of these things. And one of the goals of our work has been to take as much of that as we can, codify it in theory, and then turn it into programming tools.
So if you have a manifest, why bother with any of the other stuff?
You don't need it. If you knew how to do this up front, you wouldn't have needed any of the other stuff. You're going to like where this is going. You're absolutely right. If you knew how to write the program properly, then you wouldn't have needed all this nonsense. It's exactly the right intuition. When can we find a program that's well written to get the semantics we want without all this cost? Is that generally possible? Is it just a matter of our programs work clever enough? Or is there some sort of fundamental limitation where coordination actually is required? That's the question I want to answer next. That's the call theory. So, learning from developers is good because it's getting us to ask these questions, which is great. You know, in developer terminology, an anti-pattern, a thing you shouldn't do, is to think about read-write mutable shared state for distributed system. Just don't do that anymore, or do it very selectively. A better pattern is what Shel Finkelstein dubbed ACID 2.0. Try to write programs that are associated commutative idempotent and therefore distributed, okay, or distributable. There's some systems work on this to build an object library like that called CRDTs from INRIA, which I won't talk about it at length. There's developed a pattern called event log exchange, which is roughly what we just saw. So the question that Ron is asking essentially is this first question, which is, can I always write code that follows these patterns and does what I need it to do? Or will I sometimes need to coordinate? And if I do need to coordinate, when in my program do I need to, and how should I best do it? Right? Because we had this conversation just now about I found a way to move my coordination to somewhere local. Right? Are there ways to kind of do that? So the goal of kind of the work, the theme was go look at these developer patterns, try to extract questions that we can prove theorems about, and then take those as inspiration for building the software libraries that people can build up on. And at some level, it's the same exercise we went through, you went through, I didn't go through, with transactions, right? In the 70s, there's all this crazy read-write stuff, and then looking at how people used it, some principles came out that led to tools that could then abstract away all that complexity. How do we do that above the read-write layer now at the application level? Because that's where we need to go. Okay, so this is a theory question. Why are we coordinating? What's it for, really? And what can we avoid it? So that's what the COM theorem is asking. And I think, Rod, you're going there with me, but let me make very clear. The question we're asking is not what is coordination for in the sense of, well, it prevents races between reads and writes. That's what it's used for. But what is it really for? Maybe a better programmer didn't need that race. Maybe they could have written the program in a different way. We have to think top down here. What programs can we express? These are sort of complexity questions or expressivity questions. What can be computed if I take coordination away from you? What's the class of computations you can write? But it's also a practical question with some answers to this. Could we build libraries and languages that would encourage people to write coordination-free code? They would sort of naturally guide you to good solutions to these problems. And so Bloom is a language we've designed that's along those lines. And then can you write program analyses that, in an appropriate language, maybe, or maybe even in a traditional language, could detect the need for coordination? Could say, hey, you know what? There's a race condition there, put the Paxos there, and you'll be fine. Right, which would be nice for sort of the know-nothings. Okay, so let me talk about COM. And what's kind of fun for me as a database guy is that a data-centric view helps here a lot. The funny thing, though, is that it's not the data-centric view that came out of the transactions literature, because the answer is not in the read-write interface. It actually comes out of thinking about queries and data lineage and data flow. Okay. And there are positive results here. So the COM theorem, in a nutshell, says that monotonic programs, we have to be a little careful what we mean with our words here, but I'll talk about this in a minute. Monotonic programs can be written in a coordination-free, distributed way and get consistent results. It can be done for any monotonic program, any semi-positive data log program since Ron's in front. Just make it with a linear order, okay? F plus. So it is possible to dance with the devil as long as you do so monotonically, for whatever that means. You can get consistent outcomes without coordination. Right? And on the flip side, it is bidirectional. So if your program has non-monotonicity in its expression, if somehow it's doing a thing that is non-monotonic, it's saying something non-monotonic, then you cannot have consistent outcomes without coordination. Okay, so to achieve consistency, you must use coordination. And the intuition that we'll talk through is about sealing inputs, which you've got a flavor of in the shopping carts, right? Those manifests are like seals on our sets.
If and only
It's if and only if. The only if part's hard. I couldn't prove it, but other people could. So I gave a keynote on this stuff in 09 at Pods and got a bunch of smarter people than me interested. There's a paper that goes with that where I also conjecture that Lamport-style causality is only required for non-monotonicity. It's the Cron conjecture. And talking about, maybe we should talk about the complexity of algorithms in terms of how many rounds of coordination they need. And all of these have been followed up on by, again, people smarter than me. But much depends on definition. So when I sort of made a conjecture about this, I didn't bother defining what does consistency mean, what does monotonicity mean, or what does coordination mean. Because that's all the hard parts. That's not my job. I just had an idea. So let's take a little more time now and talk about that. So consistency, by consistency, what I really mean is confluence. That is to say, with non-determinism of message ordering, so maybe one machine is on the right and a replica is on the left. Messages diverge for whatever reason. We get non-determinism somehow, maybe through message delivery orders. And they end up in different states, one blue and one red. Eventually, over time, as data is passed back and forth between them and everybody receives the totality of the messages, they land up in the same place. All right, so that's what we're going to talk about for consistency. Upon eventual receipt of the same set of messages, you get deterministic outcomes, and all the nodes will do the same. Right, and this is both for the database, so it's convergence of the state, but it's also really convergence of the computation. There's no difference. All right, we want things you compute your output and your state to all these.
So initial consistency, you don't know when you take that. Right?
Oh, so that's an interesting point we can talk about later. Yes, unless you have a threshold function that you know locally that you've passed, which is what the seals do. Good. Sharp fellow. intuition for this. So I don't know how many of you guys here hang out with Ron and talk about data log. I sure didn't until I had to kind of came up with my work. But the way to think about monotonicity is we're going to do this in the context of logic, although you can do it also in the context of any real lattice. So think about the lattice of sets and subsets. Right? A monotonic program is going to work with operations that grow sets. Right? So in the course of evaluating the program, if you like, the sets only get bigger. If you can do that, you have yourself a monotonic program. A nice way to think about it as database folks is it's programs with select, project, join, the while loop around them if you want. Okay? It's known, and actually was proved by a student of mine, Brutal Lu, that there's execution models for this that can stream the results incrementally, take inputs as they go, and keep computing even for recursive monotonic programs. Will eventually compute the right answer as long as you feed them the data. And it doesn't matter how you batch up that data or what order it arrives in. Okay. So all that stuff, that's the easy sort of part of the proof. If your program is monotonic, you will get the same answer no matter what order the message is on. Okay. So think about growing set outcomes in your program. Non-monotonic logic, think about things where you're saying not on stuff. So negation. Actually, this is the crux of one of the proofs in one of the quant papers. Just determining if there's no participant in the distributed system that has an object, for example. Does anyone have a blue Ford? Right? There's a blue Ford outside of the meeting. Anybody have a blue Ford? You're waiting. Right? You're waiting to hear from someone. I don't know when to stop waiting, to count to 0. Right? All you want it to do is say, yep, it's 0. But counting to 0 requires knowing everybody. Right? So there's going to be this notion of sealing a set that's going to be required. That's what the coordination is fundamentally for.
Is there a connection to how easy it is to sort of, again, sample and estimate what the result is going to be?
We won't have a connection today on that. I think it's a really interesting question.
Because I noticed that the hard estimation problems seem to fall into your non-monotonic.
That's interesting. That's interesting. Yeah. I mean, it feels like there's something, the convexity and monotonicity are related somehow, right? It feels like that should help. I've thought a little bit about like some modularity and monotonicity that at least feels a little closer to discrete, but we haven't got there, so it'd be a fun thing to talk about. So other non-monotonic things, unfortunately, mutation of state is non-monotonic, and there's a simple way to formalize that in logic, which I won't do right now, but the fundamental thing that von Neumann wants you to do requires coordination as an operation. Like if truly the meaning of your program was to change this variable, which it's not, usually that's just a thing you did to try to do something else, but if really the meaning of your program was to like toggle a bit toggling is not monotonic. Set difference is negation, etc. And we know from our database implementations that you can't have streaming operators to implement these things. These are blocking operators in the database system, right? And that wasn't such a bad thing on one machine, but in a distributed system, the way you block is you wait for everybody to agree they've blocked. Okay? So your intuition as sort of database engine builders, for those of you who are here, should be, oh yeah, if it can only be implemented in a blocking way, that's a problem. I'd like people to not do that. So what programs could they write without those algorithms? So it turns out join, there's streaming parallel joins. The pipeline hash join from bullshit neighbors, right, showed that join is not one of these algorithms. It streams, it's fine. You get a non-blocking parallel join. Right? And in fact, you can do it with recursion. Okay, so much for monotonicity. So what's the problem with monotonicity? I hinted at it. It's all about time and space and all the distributed system stuff that people love to talk about, and sealing. So non-monotonicity requires sealing things. If you say not exists an item in the cart that's fragile, or no one owns a blue Ford, you got to wait for the answers because it's exactly the same thing as it's saying by De Morgan's laws for all items in the cart not fragile, right? So the only way you're going to compute a universal quantifier is to talk to the universe, right? To talk to everybody. So we know that that's going to require being able to say, yes, I have talked to everybody. I know everything. There's nothing new to know. Once I know there's nothing new to know, I've sealed the world, and now I can make decisions. Right? Time, and this is one of the, I think, big things about the paper and why it relates to a complexity model. Time is, why do we have time in computers? For this. Otherwise, we don't need time. Everything could just run in any order. In fact, it could run simultaneously. The only reason we need time at all in computing is so we can say there was a before and an after. And the only things we ever need to say before and after about are things that are not monotonic. So that seems interesting. So what's space if that's time? Well, oh, sorry. So there's this great quote. Time is what keeps everything from happening at once. It's very, very like technically true. Like that's a mathematical statement. It's great. Space is just a multiplicity of perceptions of time, and this goes back to Lamport, right? The whole idea of a distributed system. It doesn't matter if it's on a chip or it's spread across the world. It's that people have different perceptions of time, and the only way you can know what step someone else's program is at is by asking them. And by the time you hear the answer, you don't know what step the program's at anymore. Okay? So space is just lots of clocks. And so coordination is sealing across this space-time. It's global consensus on the final contents of piece of state. It's the thing that in a distributed way lets you talk about the era of before ending and the era of after beginning. Right? And that's what two-phase commit, Paxos, and so on are doing. Cool. Okay. Oh, and Zookeeper if you're a distributed system. So here's a question that people in the audience may already know the answer to. So I said, oh my gosh, all you can get are monotonic programs. That sounds awful. Select, project, join. What the hell could you compete with that? Right? Not very much, it would seem. But fortunately, people older and smarter than me have thought about this before. And if you assume, like, maybe that your data is from an ordered domain, like the integers, or you have some source of order in your computer somewhere, somehow, actually you can get all polynomial time. So monotonic programs for a suitably, a practical and suitably a generous definition of monotonicity give you all polynomial time. So any polynomial time algorithm could, maybe with a big constant factor, I don't know, could be computed without coordination in an eventually consistent fashion. That's pretty cool. It's a nice thing to know. So maybe time doesn't matter so much, because remember, it's the thing that prevents everything happening at once. It's the thing that defeats parallelism. Parallelism is all about doing everything at once, right? So we want to get rid of time, and we can. We can have all of polynomial computation without before and after. All right, so that's an intuition. There's been like a little cottage industry of papers now on this topic in terms of proofs of the Calm theorem. Best paper at Posits here actually was on this topic. Tom Amalou over in Belgium has been doing a lot of this work. He's a postdoc now somewhere else. I can't remember where. Smart guy. The Krein conjecture, which is this conjecture that causality in the Lamport sense is required only for non-monoticity. So Amalou has this paper in which he both says it's not really true, but if you kind of turn your head sideways and redefine some of the terms, then there's a thing that's true that kind of sounds like it. So we'll give him credit for it. This is both true and false. And then Dan Susiu and Paris Koutros, who's on the job market this year, by the way, have been writing papers on evaluating the complexity of, say, MapReduce style algorithms by asking truly how many rounds of coordination, how many reduces do you really need? Unfortunately, MapReduce conflates coordination with networking. Like you can't do any communication in MapReduce without coordinating, which is broken. So the Google MapReduce model is actually, unfortunately, very broken in this context. But if you built a sensible MapReduce where the mappers could stream data to each other, and then reduce was just for coordinating, then they're answering the question of how many reduces do you need, which is the same question as how many rounds of coordination. So Tom Amalou had a survey of all this stuff this past summer, which is great for sort of one-stop shop. Wow, we're super out of time. So I think what I'm going to kind of do is jump way ahead. Let's see how far ahead. I'm just going to show you. So Bloom is a language we built that encourages this style of programming. It's a disorderly language, if you like, of data, space, and time. So it's really a variant of Datalog. And why is it a variant of Datalog? Datalog is a language of sets. Sets are unordered. That's the right data structure to start with. You're going to build a distributed, and MapReduce also, right? All interesting distributed systems should be built on sets, not on lists, which is what functional programming languages are built on. Not on mutable memory, sets. Right? And then with sets, what are the operations on sets? That's logic. Okay. So you start with logic, and you have a very nice sort of database-oriented view of the world, which is great, very data-driven. But you still need to think about time and before and after. So you have to capture that in the language. So Peter Alvaro, my student, had a Datalog variant called Datalist. That's a logic of essentially space and time. We can talk about the locations of objects. You can talk about asynchrony. You can talk about sequential operations at a given node. So you have the sense of time. And then we extend that with lattices, so it's not really just sets. It's actually anything that's commutative and associative. And I won't get to talk about that more, but there's a number of papers here. The language is very easy. It looks like little merge rules. And expressions on the right are merged into state on the left, which is really just Datalog. Okay. But the merge rules have temporal semantics. So there's time, and you're allowed to add and delete things. But additions and deletions don't happen now. They happen next, which means that every moment in time is immutable. Okay, you never mutate state, you just move into the future with new state. And that's really key to the language being clean. And then when you have to communicate with entities that you don't control the time of, meaning anybody but you don't know when they're going to get messages. So there's also a notion of merging asynchronously.
In principle, absolutely everything is based on sets. Set theory is the basis, and you can find everything else is defined lists, everything is defined in terms of sets.
That's true. And the implementations of lists on sets would contain all non-monotonic stuff, right? And you're sort of saying the same thing from a very different headset that most people have.
Oh, there's a surprise.
But you're 100% right, we're agreeing with each other, just came at a different angle. So remember the who DSL, you know, if the user knows the domain, all they want is a notation for the semantics, right? So just a quick argument that Bloom is a fit language to distributed systems. The right-hand side is Wikipedia's description of a vector clock, which is a key distributed systems protocol. And the left-hand side is the Bloom program for vector clocks. And honestly, I didn't cook this very much, but it's pretty much a one-to-one correspondence of lines of Bloom and sort of statements or constraints in the English language description of vector clocks. So at least this is an anecdotal piece of evidence that somehow we got the right DSL going on. Right? And it is clearly anecdotal, and there's more you can do to evaluate this in a comprehensible user study. But we built a bunch of stuff in this language, significant things like Hadoop file system was built in this language with replicated masters and partition masters and all the hard stuff that the Hadoop guys still are working on delivering. We did all that in like 2 months because we had the right language. It was really easy. And we've also been teaching a class. I've been teaching distributed systems to undergrads with Peter Alvaro, my student who's graduating this year. And we've done this twice now. And you can teach them a protocol from the literature, and then you can put the code on the screen because it's 6 lines long, and you can talk about why it works by pointing at the code, and then you can run it. Which is really, really nice. That course has been really fun. Okay, so you can build from a better model. You can get people to write application level code that does what you want it to do by giving them better tools. They don't have to do it in Java and turn their head sideways and think really weird and not be sure they're right. And so what I'll say is that I've, 2 of these guys are on the job market this year. So Peter Alvaro, the guy at the top, he can take Bloom programs and do column analysis, figure out where are the points of order, places we need to do coordination, and then synthesize coordination. The whole idea of sealing came out of Peter's work, that I did manifests. And trying to use manifests as often as you can by following key foreign key constraints through your data and your rules. He's also been working on not randomized testing for fault tolerance, but principal testing for data lineage and fault tolerance. Very interesting work. And then the guy at the bottom, Peter Bayless, also on the job market, has been looking kind of more bottom up on how do you build, what kinds of transaction models can you indeed build without coordination, what isolation levels can you get? And if you wanted to work in the transactional world, how would you get confluence of database invariance with transactions? And it's sort of a complementary paper to column, actually. It's interesting, we haven't quite worked on how they fit together. I'm now 10 minutes over, which is 10 minutes less time than I allocated. Because we got about 20 minutes late start. But you guys are all supposed to be this, right?
We have till 11:30. You're the one with the.
So the question is, do we want to chat for 15, 20 minutes? Or do you guys want to change topics entirely and hear more stuff?
What's the more stuff?
The more stuff is the data wrangling stuff.
Yeah.
Yeah?
Yes.
Sure. So I won't talk so much. I'm going to more show a demo. But bottom line, when we did a user study, we went out and talked to analysts, my HCI friends and I. So Jeff Herons, Sean Kendall went out and talked to data analysts. How do you spend your day? And you think that they spend their day like running big engines, Hadoop and SQL. Or maybe they spend their day in R and MATLAB or Tableau or whatever the thing you guys bought. I can't remember which one is IBM's now, BI tool. Cognos? Okay. Yeah, they're all the dollars are spent. Yeah, right, SPSS, Cognos, thank you. I had a Microsoft version of the slide. I should have done the IBM version, I'm sorry.
It's fine.
Fine. Actually, I did a deck for Ginny Rometty, and I did have all the right products on it, so there you go. That for you guys. You take me on faith. Really, the truth, though, is that you spend all your time in the middle. And this is sort of 80% of your work in any data project is preparing the data. This is such a canard. Oh, so we studied this. We actually did a study. This is a very nice paper. It's a HCI paper. It's a user study of 35 analysts, asking them how they spend their day, categorizing the kind of answers they get about where are the bottlenecks in their job. Okay. People with various titles across various companies. It's really actually quite a nice paper for being able to point at least a piece of academic literature that validates that what people are saying in the markets kind of makes sense, that like the tooling for what people do today is just awful. It's awful. But you know, there's such a canard that Big Data Borat goes through this, right? In data science, 80% of time spent preparing data, 20% of time spent complaining about data. So, we hear that, but I hear it from customers too. It's not a joke, actually. This is what Trifacta customers say as well. So I'm not going to read you the quotes from the VAST paper. You can take my word for it. What's going on phenomenologically, I would say, is this. We got lots more data than we used to have. We used to just have business system data, and it had schemas, and you could map columns and stuff. But now we've also got machine-generated data and log data, and new data keeps pouring into organizations all the time, whether they acquire it themselves through their own infrastructure, or they buy it actually from others, or they get it from partners. So more data source complexity. And then the weird thing is that we're building data products that are more and more sort of consumer-oriented. So if you're building a recommender or a fraud detection system, everybody can understand what that is. So how are we getting from a world of harder and harder data sets to easier and easier data products? The answer is somebody's in the middle working a lot, right? And we want to facilitate that person because they're generating enormous value. Right? The problem is what that person ends up doing is you have so many different inputs, so many different outputs. That's not an algorithm, that's a person, right? Because there's just, this is what programming languages are for, right? They have to write code to transform the data and then to maybe write some algorithm to get from the left to the right. Right? So data transformation is fundamentally a programming problem. And I think there's a real desire to turn it into a semantic problem or an algorithms problem. It's a programming problem. It's the diversity of inputs and outputs. That's right. That's what computer programming is. Okay. So we had DSLs in the 90s for data transformation. There's one here called Schema SQL that Shankar Raman taught me about because he found it in the literature. And they said, great, we can get a DSL for this. It'll be SQL plus second order logic because you have to turn metadata into data, like data to metadata. It's like pivoting does that, for example. Oh, and we're going to need some proximity methods. This is the 90s, so it's not cast in the terms of machine learning. But you know, cluster stuff and fuzzy joins and text matching, and we'll need some of that too. So you end up with actually a really, really big language. It's harder than SQL. And the DSL approach really sort of hits a brick wall. So Shankar Raman and I worked together, and it's mostly his work really, at Berkeley in the early 2000s. Shankar built a tool called Potter's Wheel that tried to say, look, let's get a DSL that's more step-by-step and not so declarative, because people want to see the intermediate states. They need to think through this as they go. It's an iterative process to figure out how to turn your inputs into your outputs. And for every step in this language, which should be appropriately scoped so that you get meaningful visual feedback on the outcome of that step, that will help you decide if it was a good step and help you decide what to do next. So what Shankar was doing was designing essentially an algebra that had a natural visual representation of its outputs. It was at the right semantic level for people to make sense of it, and you got this immediate visual feedback. And in the background, Shankar was running some simple discrepancy detectors, outlier detection, type detection, things like that. So a lot of times it's string data to show you where the noise might be in your data. And if you get an algebraic language like this, you're stringing together like a functional expression, so you have a data lineage there. And you can do simple things like undo and redo functionally, right? You can figure out why something crazy is in the data to some degree because you know the chain of algebraic operations that got you there. So it's really quite nice. And this work actually, although we dropped it essentially at that time, it gets cited a lot. It was cooking.
It was way ahead of its
It was way, way ahead of its time. Actually, there's a bunch of companies being launched now that are roughly Potter's Wheel. So my competition is my past, I would say. The problem is, it doesn't really this isn't entirely fair, but at some level, all the burden of specification is still on the user. So there's this really smart computer back there that's just doing what you tell it to do. Right? It seems a shame, like can't the computer help you figure out what to do? So there's none of that in here. So the burden of specification is still fully on the user in this environment. So the users sit there and they write code, and then maybe they do it on a sample, and then they run the sample of data through their code, and then a computer is used to evaluate the outputs. That's nice. Computers are used, but they're used kind of as slaves to the programmer. The programmer makes all the decisions. And so what we wanted to do, just to skip, in follow-on work I did with the guys at Stanford, this is the Data Wrangler project, is to invert this sort of paradigm and say, you know what? What we really want the user to do is be in the visualization environment. So we want them looking at pictures of data. We'll pull a sample for them, and we'll render something. maybe it won't be very meaningful, but we'll give them maybe a textual representation. We'll try to draw some bar charts, okay? And they can point at features of the data that they think are interesting, like those numerals, 1BR, 3BR. I'll highlight a couple of those numerals. And then let's use the computer to predict what it is that you want to write in a domain-specific language. So the computer will give you a ranked list of suggestions for, given that you're interested in these features, and everything else we can see about the data, and maybe what we know about you, maybe what we know about the sequentiality of steps in other scripts, let's predict a distribution of next steps you would take, and show it to you, and then preview the outcome of the most likely of those, and you can look right away to see if your data is getting better, right? And you can leaf through these suggestions one by one and see the different outputs and pick the one that makes sense to you. So now the burden of specification is being taken on by algorithms, right? And the user is much more focused on features in the data, which is kind of where they should be, because that's where human intuition is required. They understand the domain, they understand what they're trying to do with the data. Why are we spending all their energy writing syntax and thinking about, which operators in the language? So we're shifting the burden of coding to the computer. So with that, I'll give you a brief demo of Trifacta, which is sort of a mature version of this that we're building at my company. And I'll just go through a quick scenario here. So what we're going to look at is it's a telecommunications example. One of our customers is Orange Telecommunications, a French cell carrier. And this is a pretty typical customer churn analysis scenario. You have a database somewhere off on the side about your subscribers. It's all nice and neat. You can get dumps from it in CSV or JSON and load them into Hadoop. And then you get call detail records, which are streaming off of your cell towers, and they're messy log files. And what we want to do is clean up those log files. Those are per call logs, so we need to aggregate them down to per customer statistics, and then we'll look at those per customer statistics and see if they correlate with properties of the customer in an interesting way. Particularly, does call quality predict the likelihood of the customer leaving the system? Right? And if it does, I don't know, you can build more cell towers or you can send them coupons, right? It's not a joke, actually. That's exactly what you do. You give them a discount. You're like, oh, man, our service is second what they did. Okay, so here's what we're going to do. I already loaded in the subscribers data, but this was a nice clean CSV. So all I did was point Trifacta at it, and that's the output of the job I ran earlier, so that's no fun. But here's a random sample of that data. You can see it's a table, right? It's got, because we're in this scenario, we're telco people, you know that IMSI is the International Mobile Subscriber ID. Everybody knows that. That's our primary key, right? So International Mobile Subscriber IDs, and then we have things like about how long have they been with the service? Are they active or canceled customers? Those are things we might want to predict in the future, right? And where do they live? And this is all here in a nice table, and it's got some visualizations. This was a raw CSV file when it came in, okay? And we could have done this on the fly. This happened instantly. We pulled a sample from the file, and instantly what we did is we predicted 3 transformations that pulled out the rows and columns, and pulled out the first row as a header. And then we did type induction a la Shankar Raman to figure out what data types we had here. All right, and then we visualized it in ways that are appropriate to those data types. So the categorical attributes are visualized one way, the numerical attributes another, and so on. So that very quickly, boom, you get your eyes on the data. Sometimes this is wrong, because algorithms don't always get it right. That's okay, because this is like Potter's wheel, like Shankar's work. This is just a language. You can undo things and go back and see how the data looked like. Actually, if you go back and take out the row breaks, the UI warns you it's going to get really ugly, because all your data is going to be in one cell. Let's not do that. But here's maybe if the row breaks were wrong, then you can go fix them. All right, but in this case, it's an easy CSV file, so it got them right. Okay, so that's data we already put in the system. Let's look at the call detail records. That's harder. And for this one, we'll start a new project, and I'll show you how it goes from the beginning. So we're going to associate this project, which you can think of like as a view. We'll associate it with a data source, which is a text file in this case. In this case, it's small because it's running on my laptop. It's a bunch of megabytes of call detail records. And we'll pull a sample of that into the browser right away, and we'll see what Trifacta can do with it. It says, I can split it into rows on \r, and I can split it into columns on tab, and here you go. And we look at this wheel, that's not very helpful. But, hey, International Mobile Subscriber ID. It's our key. That's great. Let's get that out of there. Okay. I like the International Mobile Subscriber ID. And we start to see what we call predictive interaction now. So we get predictions on patterns to pull out of the data. It's to say, maybe what you're trying to do is extract from column 2 on 4 character upper links, 4 uppercase character strings. And that's not what I want. So I'll give you another example. Here we go. This is the IMSI in the next row. And it'll re-rank its recommendations now based on 2 training assignments. And now it's doing pretty good. It's saying, I want column 2 after delimiter before delimiter. Okay? Not only does that sort of make sense, but we can look at a preview of the outcome. This all looks good. It all looks like 208 something something. And hey, the data distribution is all 208 something something also. So we know that down below there's no jump. Well, there's a little jump. There's one mismatch value. It doesn't match the data type, which has been guessed at integer. Here it is. It's right up top. It's the header. That's fine. We'll clean that up in a minute. Okay? So very quickly, we're making progress. So we'll add this step to our script. And now over here, this little subcolumn is clearly delimited by slashes, right? Let's highlight a slash and kabam. Obviously, what we're trying to do is break things up by slashes. So that's the first recommendation. Here's a few of the outcomes. Again, this one's a time column. It's been binned very nicely into days of the month because the extent of the sample isn't that big. If it was years, it would have been binned into years and so on because the visualizations are smart. And again, there's one mismatch value, which is the header. That's fine. These are durations. There's a whole lot of zeros or low numbers, which is weird. There's disconnect reasons, many of which are missing. We're going to have to clean that up. But the formatting looks pretty good. So we'll pull that out. But one last thing I know I'm going to want in this little demo is the call type. So let's pull the call type out here. And it's saying, look, you're looking for uppercase characters, but that's not quite right. Do another example. And now we're getting things before the delimiter. And that looks pretty good. So this is the raw data I wanted to pull out of these logs. These are the features that interested me. All right, and we've got them now in tabular form, and we're going to text it. Oh, it's Apple. If you left scroll too far, it goes back in the browser. But we remembered our statement at the server. So
We have a little bit of predictions
in the current product? Well, think about how they could be done. I won't tell you everything we're doing. But what do we know? We have features that you've highlighted. You can go look at the data, proactively pull out features and use those to train. So like, delimiters, for example, tend to be common across many data sets. So like understanding what's probably a delimiter is not very hard. Understanding, you can imagine information extraction techniques that understand substrings of interest.
Is it learned?
And then the idea is that it should be learned over time. And so we're seeing very little bit of it just in the example by giving more and more examples of a pattern.
But you're starting to blend into the more sophisticated addresses, which are like addresses
Right.
in India.
And, right,
Sure,
so
that's
you can sort of pile this on, right, with richer features and richer inference over time. And then the idea is how do you surface them in the interaction model. So you saw little pieces of this, right, when I did, we get into it. Like for instance, if you pull out, well, this will work, I think. It's a tendency to treat 5-digit numbers as zip codes, because that's smart. It's not obviously zip code, but sometimes it does.
Is it learned from the user? So if you did that yesterday,
That's the idea. Yeah. So this thing should get better and better the more people use it. Right? The more people in an organization work with these tools, the better the tools get, and they become fit to hopefully the domain that your system is in. And you can do things like register dictionaries with these and other like regular expression pattern recognizers.
So would you sell a trained tool, or would you sell a tool?
Today we just sell a generic tool. It's an interesting, as we grow and get more customer experience, selling tools into verticals makes a lot of sense.
Yeah.
We're not there yet. We're just in our, we've been shipping this thing for a few months. We got our first batch of customers coming out, giving us feedback and talking about it. All right. I think we kind of stopped. I was going to join this with the other data. I was going to aggregate it up. I think we're going to just not work through the whole business case on this. Actually, let me see. What's a good thing to show you? I'm going to show you, rather than make this make sense as a holistic demo, which is what I would do with the customer, I'm going to show you guys features, because you're like feature people. So, which is what I am. Right? I only realized at my startup company that I'm a product guy. I was like, oh, is that what I am? I guess so. I thought I was a researcher. No, I'm a product guy. It's like, I don't actually care how it gets used. I don't care about customers. I just care about the product. That's, I think, what researchers are. We're product people. All right, so just for fun, let's look at some Yelp data because it's JSON. So nested data formats are fun. I don't know if businesses is more interesting than reviews. Reviews are more interesting. But the JSON comes in and proactively here, instead of splitting it into columns, we're unnesting JSON nested structures. You're guessing it. This is sort of at a high level, a tabular view of your JSON. Now, if we didn't do this, you would see, JSON and whatnot, you would see this, right? It looks like JSON. Yeah. But if you go forward a step, now you see little pieces of JSON. And if you go forward another step, you see something that feels like something you can load into SPSS. Right, so that's good. And then you can interact with these things, and because it's nested data, now when you interact with, say, this is a categorical attribute, right? So the days of the week are not in order because it's nested JSON strings. But you can do stuff like say, I'm interested in Mondays, and because it sees that it's a nested structure, it'll recommend unnesting Mondays. Right? You can also interact with the categorical histogram and say, I'm interested in these 3 things, and it will recommend unpacking all of them. So, some of the things that we thought of as controllers for tabular data actually have some nice uses also with nested data. And most of the visualizations we show you, bar charts, these data quality bars, the strings, all of those, when you interact with them, you see what you've interacted with, and that drives the predictions, right? So when you click on a bar, that means something. When you click on, what's going on with all this nullness, oh, there's an example there. Let's add this, let's add that. What's going on with all this nullness, that results in predictions, and so on. So all the visualizations are actually interactive. Part of the philosophy. What else might I want to show you? Jeff Hare built a really cool data profiling quality interface, but I have to reboot the damn thing and put it in another mode because it's in beta right now, so I won't show you that. But there's a pretty amazing data quality browser, visual data quality browser that goes with this as well. So it gives you a flavor of the kind of things that this predictive interaction model can do, and the way that we can kind of flip the coding paradigm and put most of the coding efforts back in the backend. But as I said before, and we've got some questions for you guys, if you don't have the right DSL, you can't do the predictions because the space in which you're doing predictions here is the space of expressions in the DSL. If I had to predict lines in Python, I'd be screwed. Right? What's the next line of Python I should review? I don't know. Right? But what's the next 1 of 10 algebraic operators I should suggest to you? That I can probably get a handle on. So getting the DSL right, even if users can't deal with it, hopefully algorithms can. Okay, there was a question. Yeah.
So I was curious, like when you have a larger data set, right? So do you, when you're trying this, do you use some prediction on, what kind of sampling algorithm do you use, or, what's the sample size do you get from the data?
Awesome. Great question. I love it. So you'll notice actually that when the tool gets its hands on a data set, so this is all built over Hadoop. First thing, we decided to enter the market in the Hadoop context. So and Hadoop doesn't have indexes, and finding random positions in files is kind of a pain in the butt. So the first thing we do is we read the head of the file, which by the way is what analysts always do too. And that's good because a lot of structural information is at the top anyway. And so what we've been looking at right now is actually the head of the file. You get that quickly. In the background, we pull a random sample, and when it's done, you can pick it off that menu. You get an alert that there's a random sample. But as you're pointing out, what we might want to do is, for example, get stratified samples on certain columns. You might want to know, like, I'd like to see a sample that covers Mondays, a sample that covers Tuesdays, a sample that covers Wednesdays, etc. There you start to get into a place where you want the user interaction because you don't know what to stratify on. Maybe you're interested in a sample that's representative of different days of the week. Or maybe you're interested in a sample that's representative of different geos or what have you, right? And you could guess what might be a good stratification for you, or we could let you guide it. But those are some of the questions we're kind of thinking about right now in terms of sampling, is kind of how to stratify for the user in a meaningful way so that they'll get quick views on data quality. The other thing I want to point out along these lines is we're doing a lot of visualization, we're doing some machine learning, but it's all in service of data preparation, data quality assessment, and so on. So the analytics that we do and the way we do sampling and so on, it's all to get people's eyeballs on, is the data right? And so we at least have a sort of objective function that maybe, ideas like the one you're hinting at could help us figure out. You should sample for things that are anomalous at some level in a multivariate sense. It's not exactly clear how to do that without user guidance. It's much better to get some user guidance along the way. So how much do you do proactively, how much do you do on cues from the users? It's really interesting interaction.
You suggested you could use this for data cleansing, and you hinted at little places where, like, you found a bunch of nulls or blanks or whatever. What can the user do
In what
to
sense?
cleanse the data? Well, suppose I've got a bunch of nulls, and I want to replace them with something that would be useful to me.
Got it, right. And this is where, by the way, we still show syntax. We show actually code because sometimes people need to drop in and do stuff. like that. So a little simple example. What would be a good example? The only suggestions we're getting for handling these nulls right now are keep and delete, which is sort of a shame. There should be a replace suggestion as well, it seems to me. So why don't we do that? Replace column. Well, unfortunately, it's nested, so it's a bad example because I don't want to construct a string that is a JSON map because that's too hard for me. Here we go. False. So again, it didn't suggest replace, which disappoints me, but let's replace it where it's false and make it something else. Okay, so we'll say replace column open. You see, at least in the context of where I was typing, it's got all the type ahead, right? If it said false, I instead wanted to say true. Right, and then we'll get a preview of that. We can restrict this. Look at the Joseph. So there's a fairly large algebra here, and when you click on it, you get a drop down on it from the autocomplete, and then of course, there's documentation on it that goes with it. So this Wrangle language, or DSL, is documented the list of transforms there. It's not so different from the kinds of things that Shankar was doing. There's some extra stuff to deal with kind of 2014. Yeah.
I'm still a little bit unclear about how this fits into sort of the bigger machine learning pipeline. Like, for example, if I want to do something very clever about missing entries, it's like a matrix factorization or something, fill in the things, then I really want to do that and go back to this view. And now I'm worried about how does this feed into my Python system, and how do I feed that back into your system, and somehow. So this is very nice for the first step, but how do I go from there?
I love the question. You're not going to like the answer very much, I think. It's pretty pragmatic. So just to amplify, maybe for those of you in the back of the room, there's certainly many cases where you're preparing the data only to get so far to run a more sophisticated, say, SPSS or R or Python program on it to clean the data some more, after which you're going to have to come back to here to do some more stuff so that you can do the thing you really want to do. And these feedback loops between, data prep, which is a terrible word because it sounds like it comes before data analysis, and then data analysis, and then you go back, and there's feedback loops all over the place. Oftentimes you don't get to realize things are messed up until your visualization of the outputs of your machine learning models, and then you're like, oh, that looks completely wrong, I don't know why. Maybe it's the model, maybe it's the data wasn't clean. And all this stuff is intertwined, and people in the field deal with this all the time. It's terrible right now. So really what you'd like is you'd like this whole ecosystem to be integrated. That's a lousy thing for a small startup company to do. And actually it's a pretty crummy thing to write a research paper on because you can't solve it all at once. But incrementally, you're absolutely right, that's where you want to go. And you can start that mission from various points. Like if SPSS could decide they want to add these kind of features. And like SAS has this whole, a lot of our customers, the way they do data cleaning is they do it in SAS. It's awful. I mean, the SAS data step, it's called the data step. It's a sub-language of SAS that's for all this junk. And it's awful. But you can try to solve the problem from any point in the pipeline. I happen to think that starting it early in the pipeline is a nice place to go because you learn a lot from your users. You see a lot of diversity of data. And you solve a critical pain that's not being solved in the market.
So Joe, thank you very, very much.
Thanks for having me.